it's Enis Barış Bulut, and I'm working as a doctoral researcher in Trakya University. I also have my own research and development company in my university's technology development area, and which name is Vitronic, as you can see in the logo. And here is my academic page for you to check, and also here is the new web page of Vitronic with the new logo. And also, I decided to present my software skills on both MATLAB, Python, and HTML to you with this short video. So the thing is, one of the main works that I presented in IEEE Access as a journal paper can be found here. So you can see that the optimization tool is presented here, and these are the MATLAB versions results, some results taken from the MATLAB version, some algorithms that I developed, some models that I developed, and here is the experimental verification of the results of that tool. So the second verification is presented in APEC last year. So in APEC USA, I mean. So we already proved the accuracy of that tool 2 times till now. So here is the new version of the tool. The engine behind is mostly Python, converted from my previous MATLAB studies that you can see here. So let me introduce to you. As I said, these are all developed by me, so here is the system level optimization part, and here are the sub functions, so you can directly use these sub functions, but I just want to show you that optimization part because it's the most complicated part. Here is the totem pole PFC automatic design and optimization tool. So you can just increase the level as long as you want. You can just increase the interleaved legs, number of interleaved legs. So here we can see we can just adjust and just put the inputs which we want to design our totem pole PFC. So these design priorities should be between 0 and 100 because the resulting design space, as I already explained in most of my papers, the resulting design space will be probably will have 3 billions of results according to number of FETs, PFC cores, CMCs you selected. So therefore, we have to put some priority for the weighting function. And let's say it's 3 kV with 400 volts and European Union grid values, and let's say 40 degrees Celsius and for ambient temperature. And you can see these are just updated and turned to color green. So therefore, if everything is green, that means the design button will be clickable. So let's say that 35 between 55 kilohertz is okay for us, and just search the optimum point by 5 kilohertz of step size. So you can just make it 1 or 0.1 even. However, it will take too much time for that short video. So let's say maybe 80 to 120 with 10 microhenries of steps. And here there are some optional inputs, current densities, so allowed temperature rise, core height for size restricted applications, EMI filter classes, selections, and operating temperature for the semiconductors. And these number of FETs in parallel means that in low frequency FETs, using 2 FETs in parallel is a common approach. So you can just increase that as long as you want, as much as you want. However, this part is very important. This is based on a model that I presented in PCIM Nuremberg 4 years ago. This overshoot limit is relying on my own gate drive strength comparison method, which is developed and presented before, as I said, by me. And if you say that this 20% voltage overshoot limit, if you put 20 or 25 here, that means the voltage overshoot on your high frequency FETs will be limited by 25 with the automatically optimized and adjusted gate drive resistance. gate drive resistance, sorry. And therefore, if you want, you can just put a fixed gate drive resistance, or you can just say to my algorithm that the overshoot must not exceed 20%. So it will select the optimum gate drive resistance for each FET that it checks and calculates. So here just we have just databases left here. So let's start with FETs. For example, these are EPC and or maybe GAN systems, whichever you want. You can check the values from my database directly. For example, I decided to use this one. Let's say here it's fixed by me, you can see also. But for example, in PFC, I don't have that much knowledge about that. So for that, I just want to select all coolmu components. So it will check all 86 PFC cores with potential designs one by one. So in common mode choke CMCs, these are all Ferox cube components. So just let's select everything. And in bus caps, I have some from TDK and Kemet. Let's check if you have any idea. You can just directly select, or you can just leave it as it is for algorithm to select the optimum one. So here heatsinks are also selected. So you see that everything turns out to be green. So now design button is available. And as it's already fixed, you can see this EPC 2215C, but the others one will be optimized. If you want, we can just select everything here, but it will take too much time for this short video. So let me just click the design button. It will take maybe 10 or 15 seconds at most. This design process takes months and months for too many engineers. So therefore, these electronic design automation tools are very, very important, I believe. That's why I want to shape my career on these electronic design automation tools. Here's the result after just 25 seconds passed. Here you see the resulting efficiency with details, the resulting volume with details, cost with details, and it select 45 kilohertz and 80 microhenries. This box power density is of course theoretical because we have relays and some rectifier diodes, etc., controllers, sensors, varistors, etc. We need too much things, so this will drastically decrease. But these are just calculated with these 5 major components to compare in a fair manner. So you can just click on these names, or you can just click these names. Sorry for that, magnifier symbols. So let's start with the high frequency FET. So it's 45. For low frequency FET, this is IPZ, and this EPC is also decided by our user, which is me for now. And these are the details you can see both in bar chart or pie chart. It depends on you. And if you want, you can check the PFC core part. And this is also designed. It says that you just need to use CoolMuse this core with 31 turns, 2 layers with a WG10, and the cost is predicted according to Dr. Burkhardt's PhD thesis, which is written in the ETH Zurich. And so it's a reliable method, and therefore the core and copper losses are here. So here are the graphs, so you can check the input current ripple, which causes core loss and DM noise here, and this is also used in the EMI calculations, and also this is your input current. And here are some FEM solution parts, but I'm just working on them. You'll see here still in MATLAB I have some FEM core analysis, which is using FEMM 4.2, which is free and easily accessible by the API. So therefore, it's just under development. Sorry for that. I couldn't finish it yet. And also in EMI part, I have my own DM and CM estimation parts. Of course, these are estimations. DM is calculation, but the thing is, CM is estimation because common mode noise is have its own uncertainty. So without finishing your PCB design, you cannot estimate the parasitic common mode capacitance. Therefore, it's just arbitrarily selected. There is an arbitrarily selected 100 picofarad behind that, and according to this DVDT, it just uh, calculates the EMI noise, and you see that the R gate is decided to limit maximum voltage overshoot that we will see on the high frequency FETs. So these are all connected. That's why it's a very complicated thing, and you can see that your CM capacitance, which is CY, your CX capacitance, your DM inductance, and also your CM inductance and common mode choke are all designed by my algorithm, and the volumes are also calculated. So maybe I can use this part also for bus caps. I have this option here also for bus cap. It's 12 in parallel. So to be honest, the capacitor database is very narrow, so it could be better, but the capacitors in the database should be increased in number. So price and ESR losses are here, the volume are here, and also heatsink is selected from the Alpha Nova Tech components, and these are some units are also shown here. So these are just the results that we see. Here is the brief result, as I said, and these are all rely on my own methods, my own papers and conferences. And you can see these two gentlemen here, the name of these two gentlemen, which is my PhD advisor and co-advisor. So therefore, these work are all these work are done for my PhD. And after that, I decided to make it like a tool which I can share with the researchers and engineers from the industry. So it's still under development, but I mean, I could be a very advantageous candidate for your postdoc advertisement. That's why I decided to create this short video. I'm pretty sure it's not the shortest one, but as this model is too complex, I have to take your time a few minutes more. So I'm both skilled in MATLAB. I'm very familiar with MATLAB and also Python, and also this type of Flux server things. Therefore, and you can see that all these hardware in loop, I mean the hardware parts, even coding the controller is done by myself. Therefore, even these experimental results are taken by myself. So I'm both experienced in hardware and software development. So these are, you can see, these are my models and previously developed, how can I say, the algorithms. Therefore, I just want to thank you again for watching my short video, and I hope we will meet again in any future projects. So I will be eagerly waiting for your reply. Thank you so much.